It's a great pleasure to present the latest achievements in the area of 3D and 4D printing, some of which are listed in this special issue. This slide gives an overview of the main challenge we're trying to address utilizing additive manufacturing. It's called the 5S challenge for most wireless and RF structures, which means scalable, sustainable, speedy, secure, and smart. And to do that, additive manufacturing has played a really critical role in developing zero power, integrating harvesters or wireless power transfer systems, environmentally friendly, which means involving substrates that are friendly to the environment or even biodegradable, self-healing, meaning that even if there are issues due to cracking, due to bending, the structure has to work, as well as enabling morphing, as we call shape-changing characteristics, utilizing origami or other principles, and also fully printable flexible hinges for the first time, enabling structures that could adjust their shape, adjust their configuration based on the environment nearby. And that has led not only to fully additive manufactured antennas and modules, but also a new generation of meta surfaces controlling the direction of the waves, as well as reconfigurable intelligent surfaces. We're not limited anymore by planar or rectangular structures, as you can see at the top left. It's a spherical, fully printed module monitoring the quality of water. On the top right, you can see the new generation of modules with lots of new features. For example, integrated now fully 3D antennas, corrugated horn antennas, embedded fingerprinting resonators and sensors to add another degree, another level of authenticity. Being able to embed dies or even chiplets of different sizes, printing on-demand cavities and not getting limited by previous cavity sizes, as well as integrating thermal solutions by printing micro channels in full 2D, 3D implementations. Also, harvesters are really important. Integration, as you can see in the middle right, of multi-form ambient energy harvesters, power management unit, as well as sensors is now a reality. In addition, tile-based scalability is now another way that additive manufacturing 3D and 4D printing has enabled. By just printing numerous self-similar or even different tiles, you can populate very large surfaces. It's not unreal to see surfaces in excess of square meters now being populated by these tiles, either on some smart city, smart house applications, or like attachment to UAVs or other conformal surfaces, for example, for digital twin industry 4.0 applications. You can see smart wearable sensors with a variety of microfluidics, paper microfluidics, standalone microfluidics, you can see in the middle bottom. And also, for the first time, utilizing ambient wireless networks, not only as data providers, but also as wireless power grids. You can see one example of printed lens here that enables collecting energy from nearby base stations and charge IoT devices. It's not unreal anymore, pretty much to print all different parts of a module, as you can see at the bottom right. Only the ICs are not printed, and you can do it in pretty much every material or a combination of different sensors. Just to give you some metrics for 5G plus 6G, when we are talking about the Internet of Things, we're now migrating to something we call the Internet of Smart Skins, being possible with the 3D, 4D structures. So thin, flexible devices with very low power consumption, maybe below 20 microwatt, that can be fully provided by ambient sources, so eliminating the battery. featuring long range, maybe to 50 meter or more, and be localizable in real time with centimeter accuracy with just a single reader for angular range. It has to work with metal, and it can be enhanced by 5G plus or 6G, pushing for further miniaturization. Just some more examples of the 5S challenge for 3D, 4D printing smart packaging. Now, the package is not the old dummy package you just use to insulate or create hermetic enclosures to your structures, but it has intelligence that can contain some sensors, some ID devices, and also self-healing whenever you have, for example, multi-chip modules or smart wearables. So the evolution over the last 25 years, if you look, start with printed wireboard to the 3D ceramics, early 2000s with low temperature Kufar ceramic, and then flexibility was introduced by LCP, liquid crystal polymer, around 2005, and 2010s, we saw structures printed on PET, paper, fabric, and so on. But now we're moving to one step further. Glass is getting even more and more prominent for applications, especially above 100 gigahertz, and also biodegradable materials. Soon we're going to see some transient electronics that can degrade by themselves. And combining this additive manufacturing feature with some, let's say, sustainability vestige as well. Just some examples of additive manufacturing technologies commonly used. There is a variety, inkjet, aerosol, 3D printing. I just chose two to showcase the case, but also aerosol and photon-based printing are quite commonly utilized. Inkjet printing has demonstrated antennas on ICs, structures on glass, multi-layer, novel interconnects like the ramp interconnects, which improve by an order of magnitude the conventional wire bonds, and they can accommodate different ramp angles, and then print whole modules. And then in terms of 3D printing, stretchable, twistable materials with controlled porosity, and also enclosures with frequency selective configuration, or also printed ramp interconnects and individual lenses are a reality, as well as on-demand enclosures to accommodate different ICs. Just some quick examples for the next 5 minutes, and I will close my introduction. That was the first fully printed autonomous wireless module in 2019, multi-layer module, which included harvesters, that included load IC, diode, multiple antennas, interconnects in different layers. That was a backscatter, RFID-enabled sensing, 5G-based IoT module at 28 gigahertz, and then 20 to 18 gigahertz tunable system on antenna for IoT, fully printed, as you can see on the right side. That's the idea of tile by tile, configurable intelligent surfaces. And definitely, you can see, you can realize different shapes, different area, different directivity, different configuration patterns, different redirection of waves, just utilizing this tile by tile scalability. And then origami introduced the first structural way of changing the shape in a way that could be described and modeled very, very effectively. You can see the beginning of this. Utilize an eggbox element with two tunable directions that can fold both X and Y. Utilizing XG printing prototype, and you can see you can change independently horizontal and vertical polarization with 4 degrees of freedom. Hinge interconnects, flexible hinges was a major step to enable the 4D shape changing structures. Interconnects that can enable the folding maybe all the way up to a 180 degrees with a very good reliability. You can see here 1,000 plus bands. Now reliability has reached to 10,000, 20,000 foldings. So that makes shape changing quite reliable. And also you see a demonstration as well of the phased array. a phased array at 28 gigahertz with virtually limitless on-demand reconfigurability states. So 4D printing now enables you reconfigurability over a continuous range, which is quite distinct by the MEMS or electronics reconfigurability that can go to discrete states. And you can imagine the capabilities coupling the morphing or 4D printed mechanical reconfigurability with electrical. It's pretty much limitless as the origami tessellations for electronic beam steering. Just some examples of how different structures you can have by just folding just one unit cell with 4 sides. That's a printed unit cell, 4 sides. Just fold in different ways. You can rotate the peak. You can create 2 different or 4 beams. You can make it isotropic, directive, pretty much everything utilizing 4D printing characteristics and controlling it. And deployability is another main issue for 4D printed structures. Space applications, portable applications where you want to keep some structure in some compressed state, and whenever you reach the implementation phase, you fold it out and you deploy it, and then you either recompress it or you let it deploy it by itself. You can see another example here of something we call the 4D printed antenna, which is compressible, squeezable. Here you can integrate liquid metal. In the zigzag antenna, you have a helical antenna, microfluidic channel here. And in addition to the RF structure, what I want to stress is with 4D printing, we can allow scaffolding like this zipper origami Voronoi structure with controlled stiffness. And that makes the structures easily customizable to different conditions. And I'll close pretty much with a couple of slides about some smart wearables. You can see here a smart bracelet fully printed. You see the different structures. That's a combination of inkjet printing and 3D printing. Inkjet printing for the antenna array, UWB1, UWB antenna array here, top and bottom. You can attach the beamformer IC. You can pattern the ground, taper the ground, and then at the bottom, you can have 3D printed substrate, 3D printed microfluidic channel to remove heat. Here you go. You can have a very efficient, now wearable, very, very comparable, and you can see the different sides of everything as well. I will close with 2 slides, which show the future. The new generation of 3D printers enables now the push of the resolution much, much lower than what we had in mind. So typically, whenever we're talking about 3D printers or inkjet printers, we're talking about resolutions maybe around 10 micron if we really push the envelope. But new printers have now allowed us to move to resolutions below a micron. Here you see a pillar array for new generation packaging for for a large number of input and output. Here you see a monopole operating at 150 gigahertz, as well as a coil antenna operating at the same frequency. So now we're pushing to sub-terahertz frequencies using sub-micron in-house additive manufacturing recipes. And that's the future. That means now we're getting into a domain that fabrication was typically limited by cost, and the cost is getting dramatically down due to the additive manufacturing, 3D and 4D printing. So just close with this one. This is the 6G, something you keep in mind about the applications that are coming in the next 5 to 10 years. Talking about multisensory enhanced reality applications, as we call XR. CRAS systems are going to be everywhere. Autonomous car satellites and all this, connected robotics and autonomous systems, wireless brain-computer interaction, as well as blockchain and distributed technologies. And the driving trends will be more bits, spectrum reliability as always, but slowly we'll start seeing some migration from aerial conventional manufacturing to volumetric additive manufacturing, spectral and energy efficiency. You will see smart surface environments everywhere. And then you have mass availability of small data and from self-organizing networks to self-sustaining networks. So effectively, what I want you to keep in mind is we will get to quintuple convergence of communication, sensing, control, localization, and computing, and possibly out of smartphone. So the idea is pushed to millimeter wave, terahertz, receivers with integrated frequency band that can switch based on spectrum efficiency, communication with large intelligence services, edge AI, integrate terrestrial, airborne, satellite networks. We start seeing even now energy transfer and harvesting, and then start thinking even about the future generation. With this, I would like to close, and I will pass the baton to the next speaker. I hope I set up the tone of what you're going to hear about.